All right. Welcome, everyone, and welcome to DRP Turkey. Today, we are starting our seminar colloquium series with Burak Kaya. Burak Kaya received his bachelor degree at Middle East Technical University in 2010 and his PhD at Rutgers University in 2016. After graduation, he worked as a postdoc at the Department of Math at Middle East Technical University, and then he continued as an assistant professor at the same university. His research interests are set theory and its application to other fields such as topological dynamics, group theory, and graph theory. And today he's going to talk about descriptive graph combinatorics, which I couldn't read the rest, but I think you see it. And if it is okay, yeah, we can start in a minute. So
okay.
Enjoy the talk.
Let me share my screen again. Okay. Can everybody see it?
Yes.
And is it better now?
It is good. Yeah.
Okay, but now I'm having a problem. I think what I'm going to do is I'm just going to try to fit this to this area. Okay, I think this is better. Can you see it now?
Yes.
Yeah. Okay. So let me start. So first of all, I should thank the organizers for inviting me to give you a talk on a recent field that I hope we will find exciting. And I just want to talk something that's relatively recent because you're doing this directed reading program, which means that you're trying to actually get into the research. So if I talk about too old stuff like from 50s, 60s, it's not going to be that exciting because what can be done has already been done in those fields. So this is like a relatively new field, descriptive graph combinatorics. And by relatively field, I mean, in mathematics, new means that 20, 30 years old. So the first paper is around, I guess, 1999. So I would say it's like 24 years old, but we have some older results. Anyway, I'm going to start the talk now. The title is Descriptive Graph Combinatorics and Automorphism Groups. So I should tell you about each of these words. So graph, you know what graph is probably from your undergraduate education. You know what combinatorics is, but why do we have the word descriptive here? Now, the descriptive is, it's coming from the field of set theory, which is called descriptive set theory. So let's start with first part, okay? So my talk has three parts. The first part is about descriptive set theory. The second part is about classical results from descriptive graph combinatorics. And the third part is about some recent results that I actually worked on myself. Not that they're that exciting, but, it's a tradition for the speaker to actually throw in their own results every now and then. So the first part, descriptive set theory. Now, let's first start with the question, what is set theory? Because many non-set theorists are actually not aware of this. People think of set theory as like a foundational system to do mathematics, blah, blah, blah. It's interesting that historically this is wrong. Set theory was born to basically out of an investigation of Cantor on Fourier series, okay? Some trigonometric series, actually. He kind of invented ordinals while working on a trigonometric series. And then, if you look at the birth of set theory and how it basically evolved, you can see that the actual motivation of set theory has always been initially investigating the higher infinite. What do I mean by higher infinite? You know that there are different degrees of infinity. The set theory is basically the study of behavior of these different degrees of infinity on its own, like in a set theoretic way, and in the context of other fields of mathematics, like algebra analysis, topology, combinatorics, and so on. Now, what kind of behavior? Because I'm saying behavior of different orders of infinity. If you're a set theorist, you have a certain perspective. You try to understand the behavior of infinity from various perspectives. And I'm just going to list three perspectives here from the perspective of ordinality, cardinality, and definability. Now, if you don't know what these words mean, it's fine. Ordinality is about basically orders, cardinality is about size, and definability is about, well, definability. Okay, now, what is descriptive set theory? Descriptive set theory is a subfield of set theory that deals with Polish spaces. Okay, I'm going to define what a Polish space is. Polish spaces are certain topological spaces. So descriptive set theory studies Polish spaces. It studies subsets of Polish spaces. From which perspective, ordinality, cardinality, or definability, it analyzes subsets of Polish spaces from the perspective of definability. Okay. Now, what is a Polish space? A Polish space is simply a completely metrizable, separable topological space. So it's like a complete metric space which is separable. But I'm not saying it's a complete metric space because I don't care about the metric. I care about the fact that it's completely metrizable. There is some complete metric giving the topology, okay? And it should be a separable space. So the examples include the usual real numbers and the Cantor space, 2 to the power n. Now, when I say 2 to the power n, I'm a set theorist, so 2 is always the set 0, 1. So 2 to the power n is this set. You take its Cartesian product with itself n times, and you put the product topology on this. So you put the discrete topology on the set, and you take the product topology. So this is called the Cantor space. It's homeomorphic to the usual Cantor set you learn in analysis. So that's that. This one is called, the third one is called the Hilbert cube. It's the countable product of the unit interval with its usual topology. So you put the product topology. And the fourth one is called the Baire space, n to the power n. You put the discrete topology on n, you take the product topology. So these are all Polish spaces, okay? Now, let's talk about something else, some very, very basic definitions from analysis. Take a set and take a sigma algebra on the set. Now, what is a sigma algebra? Sigma algebra simply means that you are taking some subsets of X. You're putting them here, okay? What you want is that the empty set is there, the whole set is there, and this thing is closed under 2 operations. One operation is countable unions, okay? So if you have countably many stuff, you want their inside this B, you want their union to be in B, okay? So this is closed under countable unions, and it's closed under complementation, okay? So that's called a sigma algebra. Now, if you have a set in a sigma algebra, this pair is called a measurable space. It's not called a measure space, it's a measurable space, because when you put a measure on it, it's going to become a measure space. So this is like a set together with sets that I can measure, which is why it's called a measurable space. Now comes the main definition. Start with a topological space, take its open subsets, and look at the smallest sigma algebra containing the open subsets. This is called the Borel sigma algebra of X. And the subsets there are called Borel sets of X. So if you have a Polish space, let's say, what you do is you have a Polish space, it says a topology, you take these open sets, you put them in a sigma algebra, and you look at the smallest sigma algebra containing this. So you look at the sets that you start with open sets, and then you close it under the following operations: countable unions and complementation. And then you get what's known as Borel sets of X. Now, if you have taken a measure theory course or a probability theory course, you must have seen these definitions. You know what a Borel set is. These are basically the sets that you care about. And we're going to talk about why that's the case. Now comes another definition. A measurable space is called a standard Borel space if this B is the Borel sigma algebra of some Polish topology, okay? So basically, the picture looks like this. At the beginning, we have these complete metric spaces, okay? Separable complete metric spaces. You forget the metric, you put the topology, and then this is a separable complete metrizable space. This is called a Polish space. Now, you take the sigma algebra generated by the open sets, you look at the Borel sigma algebra, this is called a standard Borel space, okay? So a standard Borel space is simply a complete metric space, separable complete metric space, except you don't care about the metric, you don't care about the topology, you only care about the Borel sets. You just get the Borel set structure from it, okay? Now, this is the main object of descriptive set theory, standard Borel spaces. If you ask a descriptive set theorist what you study, in 3 words, standard Borel spaces, okay? Now, why are these so important? Because of the Borel isomorphism theorem. Let's start with 2 standard Borel spaces. Remember, what this means is that these are just separable complete metric spaces, except you just take their Borel sets. You take their open sets, you close open sets under the following operations: countable union and complementation. Whatever you get, those are the Borel sets. You just take these. if you have a map between these two x and y, which this is Borel measurable if the inverse images of Borel sets are Borel. Now compare this to the definition of continuous map. In the definition of continuous map, what do you have here? You have a topology here, topology here. When is a map continuous? If the inverse images of open sets are open. The exact same thing, but instead of using the open sets, you're using the Borel sets. You're using the measurable sets. A Borel measurable map, a map is Borel measurable if the inverse images of Borel sets are Borel. Now, these are basically the maps that you can kind of explicitly write down in real life. These are the maps that we care about. From the perspective of measure theory, these are the maps which you can integrate. You can try to integrate, okay? Now, two standard Borel spaces are said to be isomorphic if there's a Borel isomorphism between them. Now, what is a Borel isomorphism? It's a bijective map, and itself and its inverse are both Borel. Compare this to the definition of a homeomorphism. What's a homeomorphism? It's a bijective map. The map itself and its inverse are continuous. It's the exact same thing, but now you're working in a different category, okay? We're working with standard Borel spaces. So we don't care about preserving the open sets. We care about preserving the Borel sets, okay? Now, here comes the Borel isomorphism theorem. This is due to Krotowski. Any two uncountable standard Borel spaces are isomorphic, which is kind of interesting because, for example, I know that real numbers with their usual topology and let's say the Cantor space, these are not homeomorphic, right? This is totally disconnected. This is not disconnected. This is connected. But if I forget about their topologies and if I'll just look at their Borel structure, then they become isomorphic. Similarly, the Hilbert cube, this is not homeomorphic to either of these. But if you just take its Borel sets, then this pair is isomorphic to this pair and this pair as well. So all these examples in the previous slide over there, these are all isomorphic if you just take their Borel structure, just Borel sets, okay? Which is why when a descriptive set theorists say reals, they never mean reals. Like if in daily life, if you hear me saying reals, I never actually mean actual real numbers. Most of the time, I either mean bare space or the Cantor space or any uncountable standard Borel space, because from the perspective of a descriptive set theorist, all these things are the same, because a descriptive set theorists only care about the Borel sets, not the topology, not the possible complete metric, whatever. So when if I say reals in future, I don't actually mean reals. I mean any uncountable standard Borel space because they're all isomorphic. Now, let's start with a Polis space. Now, we're not talking about the standard Borel space. I'm talking about the Polis space. So I care about the topology at the moment. Can I stratify the Borel subsets of X? What do I mean by stratifying? Can I kind of like describe these or like put a hierarchy of these? The answer turns out to be yes. And here is the picture of Borel hierarchy. Now, these are your open sets. And then you take the complement, you get the closed sets because the complements are closed sets. Now, if you take the countable union of closed sets, you get what's known as 0,2 sets, or in classical terminology, this is called F sigma sets. You take the complement of this, you get a pi 0,2 sets, which are sometimes called G delta sets. And yet you take the countable unions, you get sigma 0,3 sets. You take the complement, you get these. Now, you keep doing that, not countably many times, but you iterate this through countable ordinals. If you don't know what an ordinal is, it's fine. Just ignore this part. But if you know what an ordinal is, it's not sufficient to actually do this countably many times. When you go to this stage, you're still getting new sets. But if you iterate this process, like you start with open sets, complementation, countable union, complementation, countable union. If you iterate this through countable ordinals, you get all Borel subsets of your space. And this is like a hierarchy. And it turns out that in the case that X is uncountable, so X is reals, this hierarchy never collapses, meaning that at every level, you're creating new sets. And you can think of this, a hierarchy, as a measure of complexity, because this kind of tells you, like, you think of think of open sets as your basic building blocks. In order to get something in here, you have to apply complementation twice and countable unions twice, back to back. So you have to do a lot of operations. But if your set is over here, it takes fewer operations. So this hierarchy tells you how difficult to obtain a set using these basic building blocks, okay? And by basic building blocks, I mean your operations are the sigma algebra operations, countable unions, and complementation. And your basic building blocks are also like your basic sets are open sets, okay? So we have this. Now, similar to Borel hierarchy, we have what's known as projective hierarchy. But over here, we have one more operation. And that's the projection operation, which is why it's called projective hierarchy. For projective hierarchy, you start with Borel sets here. And then you take the projections of Borel sets. And then you get what's known as analytic sets. These are called analytic sets or sigma 1,1 sets. And then this operation is complementation. You take the complementation, you get co-analytic sets. And then you take a projections again. This time, this is the projection. You get this. So for example, what's the sigma 1,2 set? What you do is you start with a Borel set in 2 dimensions. You first project this, okay? You first project this. You take the set of all y, satisfying this. You take the projection of this, and then you get an analytic set, and then you take the complement. You're still in 1 dimension. Oh, I need to project this again. So I need to start with 3 dimensions. Start with the Borel set in 3 dimensions. Project this, you're in 2 dimensions now. Take the complement. Project this, you're in 1 dimension. Now you get what's known as a sigma 1,2 set. So you start with Borel sets, projection, complementation, projection, complementation, projection, complementation, okay? So you have one more operations. These are called projective sets. Now, one may think of the Borel sets and the projective sets of a polyspace as its explicit subsets, because what I'm thinking is like, my polyspace has subsets, but which are the explicit ones? In order to talk about the explicit ones, you have to come up with a notion of explicitness. What do you mean by explicit? You have to tell me what operations I can do. And if you choose just countable unions and complementation as your basic operations, you get Borel sets, starting with the open sets. If you also add projections, then you get projective sets. And the identifying these as with the explicit subsets, definable subsets, can actually be made precise in a model theoretic sense. If you don't know model theory, this is fine. If you know model theory, this is going to make much sense. Take the field of real numbers and add a predicate for integers, meaning the following. Yeah, add a predicate for integers. Then you look at the definable subsets of the structure. What do I mean by definable subsets? You write down a formula. And in this formula, you can quantify over real numbers, but I'm also allowing you to quantify over integers as well. Okay, things like this. You write something like this, and then maybe you put some other stuff, x squared plus, you're allowed to use multiplication, addition is 0 and 1, x squared plus y squared is 1, and blah, blah, blah. You write something here. Then the corresponding set, let's make this u, let's put a u here, u equals x or blah, blah, whatever. This formula will define a subset of real numbers. That is going to be a projective set. And that's a theorem. The subsets of the structure which are first order definable via parameters are precisely projective sets, sets that you can find here. And there's actually a correspondence between these things and the definability. For example, if you have a sigma 1,3 set, something here can be defined by 3 alternating quantifiers, whereas inside you have some Borel stuff. And the sigma 1,3 basically tells you that the sigma tells you that you start with a there exists, and 3 tells you that you're going to alternate 3 times. And then inside you will have some Borel predicate, okay? So there's actually a very precise relationship between this notation and definability on the structure, okay? So now we have Borel sets and projective sets, and we think of these as the definable subsets of reals. And over here by reals, I mean the actual real numbers, okay? Not something else. So we think of this as the explicit subsets. Now, what do these have to do with set theory? Because so far I have just talked about topologies and measurable structures. So you may claim that, okay, he must be a measure theorist or a general topologist because we haven't been talking about set theory. What's the connection with the set theory? Classically, three properties of R have been investigated. These are called regularity properties of reals. One of them is being Lebesgue measurable. If you have taken a measure theory course, you know what this means. Otherwise, think of this like we're trying to measure the length of a subset. We're trying to generalize the notion of length of a subset. The second property is called having the bare property. Having the bare property means that you're almost open from a topological perspective. What do I mean by this? There's a topological notion of smallness. It's called meagerness. Meager means that you're a countable union of nowhere dense sets. Nowhere dense means what? Your closure have empty interior, okay? If your closure have empty interior, you're called nowhere dense. And if you're a countable union of nowhere dense sets, you're meager. So topologically speaking, these are small sets. And it turns out that having the bare property, like this is the definition, having the bare property means the following. You're almost open. You differ from an open set by a meager set. So if you have the bare property, then there's an open set such that when you take the symmetric difference, you get a meager set. So you're almost open. And the last property is called the perfect set property. Perfect set property means that you're either countable or you contain a perfect set. Now, what is a perfect set? Perfect set means that you're a closed set and you have no isolated points. Closed set, no isolated points, it's called a perfect set. Having perfect set property means that if you're either countable or you contain a perfect set. Now, why is this important? If you know about the continuum hypothesis, which states that there is no cardinality between natural numbers and real numbers, having perfect set property means that you can't be a counterexample to the continuum hypothesis. If you have the perfect set property, you either have the cardinality of natural numbers, or if you have a perfect subset, that has to have the cardinality of real numbers, okay? Which means that these sets can't be counterexamples to continuum hypothesis, which is why this property was being investigated. Now, people were investigating these classical properties, like classical regularity properties. It turns out that Borel sets have all these properties. If you are Borel, you are Lebesgue measurable, you have the bare property, you have the perfect set property. You are a very nice set. You have all these very, very nice properties. Starting from the second level of the projective hierarchy, the behavior of the projective sets can't be decided by set theory, by ZFC axioms. And this is kind of the connection with the set theory. Here's a theorem which I think is due to Gödel. Even if Gödel didn't state this himself, I think it follows from something he did. Maybe he said it himself. Now, there's something called the axiom of constructibility. This is it. If you assume that on top of ZFC, then not all sigma 1, 2 sets are Lebesgue measurable, have the bare property and perfect set property. There are sigma 1, 2 sets without these properties. So these are like bad subsets. They're not regular. They don't have these regularity properties. They're not nicely behaved. If you assume this axiom. However, if you assume another axiom, existence of a measurable cardinal, if you don't know what this is, this is like some set theoretic axiom about existence of certain ultrafilters on certain sets, whatever, blah blah. Just ignore it, okay? If you don't know it. If you assume this, then every sigma 1, 2 set is Lebesgue measurable. They have the bare property and perfect set property. So if you ask me this, are these sets well behaved? Do they have the regularity properties? The answer is independent of ZFC. We don't know. Under one axiom, they are nicely behaved. Under another axiom, they're not nicely behaved. And if you assume sufficiently large cardinal axioms, like if you know what a wooden cardinal is, you just take infinitely many wooden cardinals with a measurable cardinal on top of blah, blah, blah. If you assume additional axioms, you can prove that all projective subsets of real numbers are well behaved. They are Lebesgue measurable, they have the bare property, and they have the perfect set property. And this is one of the connections with set theory, okay, of these seemingly unrelated objects. Now, if you're a set theorist, I'm going to show you something. And there's another slide after this, which says if you are not a set theorist. there's a famous result of Soloway, which says the following. So you may be thinking that like some people have problem with axiom of choice, okay? Like you're constructing these objects which you can't see, their existence is just like God-given with axiom of choice. It comes out of nowhere, blah, blah, blah. Now, Soloway proved the following. There is something called an inaccessible cardinal. It's again a certain very large object, okay? Now, if you are a category theorist and if you heard about grothendieck universes, basically think of a grothendieck universe like an inaccessible cardinal. They're not the same thing, but if there's a grothendieck universe, I think there's an inaccessible cardinal and vice versa. So think of these all like, this says something like there exists a grothendieck universe, okay? If you assume that this theory is consistent, meaning that you can't prove a contradiction from this, then the following theory is also consistent. You drop the axiom of choice, you add what's known as dependent choice, which is the minimal thing to be able to do measure theory, and then every subset of real numbers have all these properties, okay? And there's another result. Again, this is a very technical result. I can't tell you how this goes. You need to learn forcing some higher level stuff. There's another result earlier than this. This is like one of the first applications of forcing, a famous technique invented by Paul Cohen that actually got Fields Medal to him. If ZFC is consistent, then so is the theory ZF plus every subset of R is Borel. So if the set theory axioms are consistent, you cannot prove just by ZF axioms that there is something Borel, okay? And I'm going to talk about this in the next slide anyway. So these technical results mean the following for the layman. If you're not a set theorist, why should you care? If you have constructed a subset of real numbers without one of those regularity properties, then you must have used axiom of choice, some form of axiom of choice, and it has to be stronger than dependent choice, okay? So if you can somehow construct a set which does not have the bare property, then your proof must have used some kind of axiom of choice, which is stronger than DC. So it can't be completely explicit. Similarly, if you can somehow construct a non-Borel set, then you must have used at least dependent choice, okay? Some form of AC. Without any choice, you cannot construct a non-Borel set. Now, what are these motivating? These are motivating that if you can construct something non-Borel, you have to use a certain amount of choice, so it has to be non-explicit. If you can construct something without these nice properties, you must have used a strong form of choice, so it can't be explicit. Which means that if you're searching for explicit constructions, if you want to actually write it down in a nice way, whatever you are searching for, being non-Borel actually tells you that, like, if you know that your solution has to be non-Borel, you should think of the following. Okay, this is the number, this solution must be non-Borel, which means that my proof has to use at least dependent choice, so it can't be completely explicit. There will be some choices around. Or if your solution, you know, that is not Lebesgue measurable, then these results tell you that it can't be explicit at all. You can't just write it down explicitly. You must use axiom of choice in a very strong form, okay? So if you want your solutions to be explicit, you should care about Borel sets and projective sets. Now, this was the first part of the talk, for which I spent a lot of time. But hopefully, it's actually motivated this part. Now, we're going to talk about descriptive graph combinatorics, and we're going to talk about a glimpse of some classic, the title is a glimpse of some classical results. There are many classical results, and by classical, I mean these results are around 23, 24 years old, so just like you. So some of these are actually older than you, and one of them is actually older than me. Whatever. By classical, I mean classical, but not that much classical. So we're going to see some results, but not that much. Now you now understand the word, this meaning of the word descriptive. Okay, we're interested, like descriptive set theory is basically about projective and Borel sets. And why is it called descriptive set theory? Because those hierarchies, if you look at them, they're about basically descriptions of those sets. The hierarchies literally tell you how complicated it is to define those sets, which is why it's called descriptive set theory. And now we're going to incorporate this into graph theory. Now we're going to start with some very basic graph-theoretic definitions. Now, all of you know what a graph is, right? Hopefully from your undergraduate education. A graph is something like this, okay? This is a graph. You have these points and you have these edges between points. You have these vertices. These are called vertices. You have these edges, blah, blah, blah. Now, what's the formal definition? There are a couple ways to define this. There are a couple ways to define graphs. I'm going to choose the following definition. You start with a set. This is our vertex set. A graph is simply a pair VE where this is a relation. And you want this relation to be an irreflexive symmetric relation. Why? Because if A and B are related under this relation, you want to interpret this as there being a directed edge from A to B. Now, if this relation is irreflexive, what do you exclude? You exclude self loops. You don't want, in a graph, you don't want self loops like this. So you want this relation to be irreflexive. And when you make it symmetric, there are directed edges in both directions. So if there are if you have directions in both cases, if you have directions in both ways, you may as well think of this as an undirected edge. So making this relation symmetric makes it undirected, okay? So this is like a graph. And the adjacency relation is encoded in this relation, okay? Now, start with a graph, and let's take a set, which we shall refer to as the set of colors. Now, a vertex coloring is a map doing the following. Now, I'm going to give an example for this because you may not have seen this. This is your graph, okay? You want to color the vertices to different colors so that adjacent things get different colors. So, for example, this is a coloring of this graph with 3 colors. Adjacent things, adjacent vertices where there's an edge in between them, are assigned to different colors. So this is a coloring, vertex coloring of the graph, okay? On the other hand, if I try to color this with 4 colors, I'm gonna fail. With 3 colors, I'm gonna fail, because let's color this to red, let's color this to blue, let's color this to green, and then I have to color this. If I color this to red, this is not a vertex coloring because these are adjacent, but they are of the same color. Now, a coloring means that if there is an edge between 2 vertices, then their colors, their assigned values are different. This is called a vertex coloring. And the chromatic number of a graph is the minimum number of colors for which there is a coloring, okay? So, for example, I shouldn't have erased those graphs. So let's take K4. Now, it is clear that you can't color this with 3 colors, but you can color this with 4 colors. Let's put red here, blue here, green here, and orange there. Okay, so this is a coloring with 4 colors, but there's no coloring with 3 colorings, so the chromatic number here is 4. Okay, now let me draw another graph here. So let's see, what's the chromatic number here? Let's think about this. Because of this triangle, it is impossible to color this with 2 colors. But let me try 3 colors. If I color this to red, color this to blue, and color this to green, can I still color these? Yes, of course. I can color this to blue, and I can color this to red, which means that, now this is a coloring, as you can see, and adjacent things get different colors. And I can't do this with 2, but I can do this with 3. So the chromatic number here is 3. Okay. Now, chromatic number is something that graph theorists are very much interested in. Okay. And here is a very basic result from graph theory 101. You may not, like I said, it's 101, but maybe this is like 201 or 301. Like if you haven't seen this in your graph theory course, don't think that your graph theory course was bad because I just named this 101. Maybe your instructor was not interested with chromatic numbers. Now, here is a theorem. If your graph contains no odd cycles, now a cycle in a graph means the following. It means what you think it means. A path in a graph is you start from one vertex and you start walking around, you go through the edges. Okay, this is like a path. Now, a cycle is a path where your ending point and your starting point are the same. So blue one is a cycle, and odd cycle means that its length, the length of the cycle is odd. So here's an odd cycle. It's a cycle of length 3. It's a theorem that if your graph contains no odd cycles, then the chromatic number is actually less than or equal to 2. Now, why is this the case? The basic idea is the following. Now, I'm going to draw a graph with no odd cycles. And let's put this 1, 2, 3, 4, 5, 6. Okay. Yeah, this is fine. There are no odd cycles here, and I can color this with 2 colors. Here's my algorithm. I'm just going to choose a random vertex. Color this to color this to red. And then the neighbors of this, I'm going to color all the neighbors to blue. And the neighbors of the blue ones, I'm going to color them back to red. And I'm going to keep going like this. If I had more stuff here, now I would color this to blue and so on and so forth. So you choose something, you color it to a certain color, and then you color their neighbors to a different color and so on and so forth. Now, if you try to do this with an arbitrary, if you do this with a finite graph, it's no problem. It's doable. If you do this with an infinite graph, you have to be careful. Because your graph can have many connected components. Connected components of a graph means the following. You have your graph. You take the vertices between which you can find paths, and you call them connected components. So if this is your graph, it has 4 connected components. This is one connected component. This is the second one. This is the third one. This is the fourth one. Now, take all your connected components. Using the axiom of choice, choose one vertex from each connected component. Okay? So there can be uncountably many connected components. It's fine. By axiom of choice, you can still choose one vertex from each connected component. And now what you do is this. After choosing that vertex, you just do what I explained to you before. You choose your starting vertex, VS, okay? This is a connected component, and from this connected component, you have chosen this base vertex, base point, like a distinguished point, VS. And here's your coloring. If there is a path from your V to this VS of odd length, so if there's like a path here of length 3, you color this to 0. Okay, my colors are not red and blue anymore. I'm going to call them 0 and 1. If there's an even path like this one, you color this to 1. Now, if there's an even path and this is colored to 1, then this must have colored to 0. Okay? And then this will be colored to 1, and this will be colored to 0, this will be colored to 1. So this function is going to do exactly what I told you it's going to do. Like, it's going to do the process that I described. And here are the important parts. You may think that, like, maybe this is not a well-defined, this is not defined for every V. Because I have chosen a base point from each connected component, every vertex V can actually be connected to some VS via some path. So this is always defined because I have chosen one point from every connected component. And the more important part is having no odd cycle property guarantees that this is well defined. So you may think that this is maybe not well defined. Maybe some V is assigned to both 0 and 1. This can't happen. Why? Because if V is assigned to 0 for some VS, like that means that from V to VS, there's an even path. But if there's also an odd path, then there's an odd cycle here. Even odd, there's an odd cycle here. So having no odd cycles guarantees that this is well defined. And not only that, it guarantees that this is actually a coloring. So I can just color this with 2 colors. Okay, no odd cycles, 2 colors. Now here's an example. This is a graph from a paper. My graph is on real numbers. So I won't be able to draw the diagram because the vertex set is infinite. Not only it's infinite, it's uncountably infinite. My vertices are real numbers. And I'm just gonna make you understand it like this. So if there's an edge between my vertices, I'm just gonna put a point here, okay? And this graph is represented by the following: x minus y in absolute value equals, if x minus y in absolute value equals 3 to the power n, then you connect these two, okay? You connect these two by an edge. Now, I claim that there are no odd cycles here. Why? Suppose that there's an odd cycle. So there is this x1, another x2, another x3. It goes like this up to xn, and after xn, it comes back to x1. Then these differences must be plus minus 3 to the power k, okay, by definition of the graph. If there is an odd, like take a cycle. This is a cycle of length n, okay, 1, 2, 3, 4, n. This is a cycle of length n. And by definition, we have this. Now, multiply all sides by a sufficiently large 3 to the power k, and then you can make all these things integers by multiplying with this 3 to the power k. And they're going to be odd integers. Now, you add n many odd integers, and you get 0, an even number. If you're adding n odd integers and getting an even number, then n itself must be even, okay? Therefore, by the previous theorem, this graph on real numbers, which we can't imagine because it's like it has uncountable many vertices, this is chromatic number 2, okay? And here's a question. Can you find an explicit coloring? Because this theorem used axiom of choice, and you may think that, like, I want to see the C. Like, over here, I just constructed something, but I don't see it. I want to see the coloring. So for this very explicit graph, can you see the coloring? Can someone write down a function, explicit coloring? Now, we're gonna answer this question, but now what I'm gonna do is I'm gonna Borelize all the definitions. Okay? Now, do you remember all the definitions here? And I need to get quicker. You see all the definitions here. In front of all of those things, I'm just gonna put the word Borel and make everything Polish, okay? Okay, there are 2 people waiting in the waiting room. Let's actually admit them because it keeps popping up on my screen. Now, this time, my vertex set is not going to be an arbitrary set. It's going to be a standard Borel space. So it has a measurable set structure. My graph, my edge relation, which was a subset of the product, Cartesian product, is going to be irreflexive symmetric, but I want it to be measurable as well. I want it to be a Borel subset. So I want this edge relation to be a Borel subset now. Now, this is a standard Borel space structure. So there's a product standard Borel space structure on this, okay, which you'll learn in your measure theory course. I'm not going to go about that. So I can talk about a subset of this Cartesian product being Borel or not, or being projective or not. So now I can talk about Borelness of the graphs or projectiveness of the graphs. So a Borel graph means that you're just a usual graph, but you're not Borel. Now, my color, my set of colors, I will take them to be standard Borel spaces. And a Borel coloring is just the usual coloring, except this is a standard Borel space. This is a standard Borel space. I know what it means for a map to be a Borel map. I just want this to be a Borel map. Remember, we associated Borel maps, Borel sets with the explicit sets. So this is like an explicit map, a map that I can write down, a map that you run into in real life when you do analysis, okay? So it's a Borel coloring. It's the exact same definition. And Borel chromatic number is exactly the same definition, but now you want Borel coloring. Now, sometimes mathematicians, well, some mathematicians, there's at least one, but there are multiple, they just like to generalize stuff for the sake of generalization, which is kind of stupid. Like, if you're generalizing something, and if all the theorems that you earlier had actually generalize as well without any changes in the proofs, then you're just doing bad math, okay? Because you're not contributing to anything. If you're doing generalizations, you just want things to change. Otherwise, if you're just copy pasting the exact same proofs, that's not very exciting, is it? Like, I mean, anyway. Now, it follows from the Borel isomorphism theorem that the chromatic number here can only have these values. It's either finite, or it's countably infinite, or it has the cardinality of real numbers. This is the cardinality of real numbers, okay? Why? Because I know that any uncountable standard Borel space is isomorphic to real numbers. So the cardinality here, the cardinality of I can be this if it's not countable. So from Borel isomorphism theorem, I know that the Borel chromatic number can be either of these. Now, here is an interesting thing. When you do this generalization, things break down. There is a Borel graph which has usual chromatic number 2, but its Borel chromatic number is uncountable, which is like a huge jump. Like, think of it like this. When you try to just color it randomly with arbitrary functions, you can color it with 2 colors. But when I tell you to color it with measurable functions, with functions that you can actually see, with explicit functions, Borel functions, then it requires uncountably many colors. Why? Remember the graph we had earlier, defined earlier? That's actually a sigma 0,2 graph. The reason is this. If you try to write down the set E here, this set E is the countable union of all x, y, such that x minus y, this is n. Now, this is a closed set, and this is a countable union of closed sets. So this edge relation here is a countable union of closed sets, which means that it's an F sigma set, okay? It's a sigma 1, 2 set. And we know that that graph has chromatic number 2. We just proved that. Now, I'm going to prove that it has an uncountable chromatic number. Why? Suppose that you can color it with countably many colors. Let's put natural numbers here, okay? Suppose that you can color it with countably many colors. Then, because these are, this is a Borel map, when I look at the inverse images, these are going to be Borel sets, which means that they are Lebesgue measurable, which means that they have measure. But now, when I take the union of all these inverse images, I get all of real numbers, which have infinite measure. So these can't have all 0 measures. Some of them must have positive measures. Take one of them. Suppose that the inverse image of I has positive measure. Now, there is something called in analysis called Steinhaus theorem. It tells you that if you have a positive set, a positive measure set, when you look at its difference with itself, it contains a small interval around 0. So if A has positive measure, when you look at A minus A, and A is a subset of real numbers, this contains a ball around 0. Okay, that's literally the statement of Steinhaus's theorem. So there is such a thing. And then take that, and then find a sufficiently small, a sufficiently large k so that 3 to the power k falls into this interval. Okay, but then by definition, what's going to happen? Because this interval belongs to this difference, there are x and y such that this 3 to the power k is equal to x minus y. But that means that x and y are connected by the definition of the graph. But they are both in the inverse image, so they take the same color. But they're connected, they take the same color. Contradiction. Which means that I can't color this graph with countably many colors using a Borel function. Okay? So things break down, like things change drastically. Now, I'm going to continue. I'm going to get faster. I don't think I will be able to talk about my stuff, but whatever. This is an example which is supposed to illustrate why this thing is exciting. Because when I try to do a generalization or more of a specialization into a measurable setting, things actually break down. Does the previous theorem use CH? No, it does not. None of them uses. I haven't used CH anywhere. Anyway, there was a question on the chat. Now, let's talk about graph isomorphism. A graph isomorphism means what you think it means, okay? Okay, can you explain Steinhaus's theorem again? Steinhaus's theorem tells you this, literally. If you have a subset of real numbers, and if A has positive measure, then when you look at A minus A, which is just X minus Y, where X and Y comes from A, this thing contains an interval around 0, okay? This is literally the statement of Steinhaus's theorem. It looks technical, and it is technical, but it tells you that, okay? Now, a graph isomorphism means, if you have two graphs, just a function which preserves the edge connectedness relation. So, if A and B are related, if there's an edge between A and B in the first graph, then there's an edge between their images in the second graph, okay? So this is a graph isomorphism. Sorry, graph homomorphism. Isomorphism means what you think it means, blah, blah, blah. Now, we write less than or equal to denote that there's a homomorphism. Suppose that these graphs have additional topological or measure theoretic structure. Maybe these are Borel graphs, okay? Or maybe there are topologies. Then I can, if there are additional structure on V and W, then I can talk about additional properties of this map. If these are topological spaces, I can require this graph homomorphism to be a continuous map. Or if these are standard Borel spaces, I can require this to be a Borel map. In which case, you can talk about continuous and Borel homomorphisms. And my notations for that are, I'm just going to put a C for continuous and B for Borel there. Now, a very, very surprising and very fundamental result from descriptive graph combinatorics. You take the Cantor set, okay? Like, I'm not going to explain, I'm not going to try to motivate the theorem because it is really interesting. It is about the following. I have graphs with uncountable chromatic number here, okay? Uncountable chromatic number. What can be the reason for this? Like, why? How did this happen? There is something called G0 dichotomy that tells you exactly why this happens. But in order to state that, we need to talk about the special graph. Now, look at the Cantor set, okay? Cantor space. Now, you can imagine Cantor space is the space of 0, 1 sequences indexed by natural numbers, and you can just imagine it like the paths of this infinite binary tree, okay? Each path will give you a 0, 1 sequence. So let's say left is 0, right is 1. This path is the sequence 0, 1, 1, 0, 1, dot, dot. Left, right, right, left, right, blah, blah, blah. So 0, 1 sequences can be thought as paths, infinite paths of this infinite tree. This is going to be my vertex set. And what I do is this. I choose a very special subset having the following properties. These are SNs. These are finite sequences, okay? And so maybe I should just draw the infinite binary tree again. I choose countably many finite sequences such that Sn has length n. So for example, S0 is the empty sequence. S1 could be this. S2 could be this one. This has length 2. S3 can be this one. I choose finite sequences so that they have this additional denseness property. Any element in the Cantor space is an extension of some sk. So for every x in the Cantor space, there is some k such that when I restrict this sequence to the first k letters, first k entries, you get sk. Okay? And the G0 graph obtained from this is defined as follows. Two sets in the Cantor space are connected. Two sequences in the Cantor space are connected if the following happens. There is an n such that when you restrict this these to Sn, you get the same thing. When you restrict these to n, you get Sn. And then at the nth entry, they differ. If this is 0, this is 1. If this is 1, then this is 0. And afterwards, they're the same. So what this does is the following. So suppose that this is S3. Okay, this is S3, this finite sequence. Look at the following paths. I do the S3, and then let's say I go left, and then I just go zigzag. Now, at this point, I made a left and I did a zigzag. Up to that point, I did the same. Now I'm going to do a different, like instead of going left, I'm going to go right. I'm taking care of this part. And then afterwards, I'm going to do the exact same thing. I'm going to go do a zigzag. What I'm doing is I'm connecting these two paths. Remember, my vertices are the paths themselves. So between these two paths, I put an edge, okay? So these SNs, they tell me which things to connect. So for example, when I take this one, I do a left and I do a right. And when I do some zigzag, if I do the exact same zigzag after this, I connect these two by an edge. This is called the G0 graph, okay, associated with this. And here's a very, very interesting theorem. And this is like the first, it is in the first paper. Suppose that you have an analytic graph. Analytic graph means that you're an analytic subset of product space. Remember, we talked about Borel graphs. Now I'm talking about analytic graphs. So you have a polis space, you have an analytic graph of the polis space. Then we have this either or statement. Either your chromatic number is countable, or if your chromatic number is not countable, there is a very good reason for that. And that reason is this G0 graph continuously, continuously, I should say embeds into you. It's just a homomorphism, but there's a continuous homomorphism from this G0 to G. So this G0 is like a blockage. It has uncountable chromatic number. So if it's inside a graph, if you find a homomorphic image of this G0 inside the graph, then it has to have uncountable chromatic number. And the theorem tells you that this is precisely the reason. If you have uncountable chromatic number, it must be because this G0 continuously homomorphs into you, okay? And this is very interesting. Like in usual graph theory, when there's no measurability conditions, we don't have any result like this, okay? You can't just tell, oh, I have uncountable chromatic number because this happens. You don't have this. But in this setting, we have this very interesting dichotomy theorem, okay? Okay. Now, this is called the G0 dichotomy. So this tells you like your Borel chromatic number is either uncountable or disembedded to you. And like 2 years ago, they proved a similar result for this. If you have an analytic graph on a policy space again, there is something called L0. This is much more complicated than G0, so I haven't defined this. They prove that either your Borel chromatic number is less than or equal to 2, or, okay, I forgot to change, this was like on a Turkish slide, so I forgot to change this to or L0 continuously homomorphs into you. So it's the exact same theorem, but over here, instead of LF0, you have 2 there, okay? You have 2 there. Now, after this, one of these authors, and Steve Todorchevich from Toronto University, a very famous satirist, proved the following. Such a result cannot be, such a basis result cannot be obtained for other things. Like you can put 2, we have the result where we have 2 here, we have a result where we have LF0 here, and they prove that you can't have such a graph for 3, 4 dot other things, which is kind of interesting because for countable chromatic number, you have a dichotomy theorem. For chromatic number less than or equal to 2, you have a chromatic dichotomy theorem. And it turns out that no such theorem exists for other things, which is like a very surprising result. By the way, my master's students and I were working on trying to get this for 3. And now we found this paper and we were like, oh, we're trying to prove a result that can't happen. And then we stopped working on that. Anyway. So this is like a very interesting result to surprising dichotomy theorems. Now, I'm going to like this. Remember, this slide was about when things break down. Over here in the usual graph-theoretic setting, like chromatic number is 2, and then it becomes uncountable when things break down. It turns out that things don't always break down, okay? And after this, I'm going to, by the way, finish. I don't think I'm going to start the third part of the talk. Now, there is there's a notion of edge chromatic number. It's the exact same notion, but then this time you are coloring edges. And what you want is that if 2 edges are adjacent, you want to color them to different colors, okay? You want to color them to different colors. So this is like an edge coloring but now this is not an edge coloring, okay? Because these are like green, and they have a vertex at the intersection, okay? Now, you can define edge chromatic number. Edge chromatic number is the minimum number of colors that you require, blah, blah, blah. It turns out that if you have a locally countable graph, then its edge chromatic number is countable for very basic set theoretic reasons, like countable reasons. Take the connected component, okay, of a locally countable graph. Locally countable means that from every vertex, only countably many vertices are to any vertex, you only have countably many vertices connected to. So if you're locally countable from this, you can only have countably many edges going out, okay? Now take a connected component. Then in this connected component, there can be only countably many vertices. Why? Start with this, take the ball of radius 1, and then take the ball of radius 2. Because of this local countability condition, at every stage, the number of vertices that you will have is going to be countable. And then if take all the possible radii, countable many radii, countable union of countable sets is countable, you can have countable many stuff. But if you have countable many vertices, then you can only have countable many edges between them. So if in each connected component you have countably many edges, just color them to different colors, and then you will have a coloring with countably many colors. Okay, so this is like a very trivial result. It turns out that the exact same result holds for a locally countable Borel graphs on centered Borel spaces. Now, this time you have to generalize this concept. So you don't have edge chromatic numbers, but you have Borel edge chromatic numbers. So you still have Borel colorings, blah, blah, blah. The exact same result holds, but it turns out that the proof is much more difficult. Now, because of the time constraints, I'm just gonna skip the proof. This is in the first paper, but let me tell you why this is exciting. Like, this proof was just a cardinality argument. This is like very simple. When you try to prove this in the Borel setting, I'm just going to skip some slides. You need to talk about Borel constellations, and you have to use something called the Feldman-Moore theorem, which is like a deep result itself on its own about Borel group actions, blah, blah, blah. And then you do very smart stuff with involutions in this group and blah, blah, blah. It works. Now, the theorem generalizes. However, the proof itself does not generalize. Like, the proof is much more complicated. Okay? But the theorem actually generalizes to that setting. Okay, so things don't always break down. Now, I think, can I have 10 minutes?
Yeah, sure. Yeah,
sure. Then I can actually finish the talk. Now, so this was one example when the result actually generalizes from usual graph theory to Borel graph theory. Okay, descriptive graph combinatorics. Now, this is like my master student and I were working on this dichotomy theorems, and we were trying to prove something that can't be proved because it was wrong. There was no such graph there was no basis result for chromatic number 3 there. And then we switched topics and thought, like, what should we do? And he was already interested in automorphism groups of graphs. So we thought that, okay, well, let's work on Fruit's theorem, and then let's try to generalize that. Now, Fruit's theorem is a very classical theorem from 1930s. It says that if you have a finite group, you can realize this as the automorphism group of some graph. So if you have a finite group, then you can write down some graph whose automorphism group is that finite group, okay? And then later on, Deguit and Sabirusi independently removed this finiteness condition. Every group is isomorphic to the automorphism group of some graph, okay? And the proof idea is the same. It's always the same. It's a very elegant idea. I'll talk about this because I think it's very cool. Like Fruit, like this is a very good idea. You start with your group, and then you take a generating set and you construct its Cayley graph. Because of the time constraints, I'm not going to explain that. But if you know what a Cayley graph is, like your vertices are the group elements. Okay, this is the identity. This is something else. This is something else. And for everything in S, for every generator, you put a directed edge, okay? And you put a label. If A is inside this, you put this. If B is inside this, you put this. And this is the element A, this is the element B. And for example, this is the element AB. You have these directed labeled graph, okay? The Cayley graph is not a usual graph here. It's a directed labeled graph. So every edge has a direction unless S is symmetric. And every edge also has a labeling, okay? Now, you look at this as a directed labeled graph. And when you compute the automorphism group of this graph as a directed labeled graph, so you're not looking at the usual automorphisms, you're looking at the automorphism, you're looking at the directed labeled graph automorphisms, meaning that your isomorphism should respect directions and it has to respect labels as well. Then that becomes isomorphic to the original group G. But now I don't want a directed labeled graph. I want a usual graph, okay, a regular one without all these fancy stuff. If you just take this directed labeled graph, and then replace these directed label edges systematically by asymmetric undirected graphs. Asymmetric graph means that you have no automorphisms except the trivial one. So you're an asymmetric thing. You don't have any symmetries, okay? Your automorphism group is trivial. What you do is you just go to these directed labeled edges and systematically replace this with stuff. So between these two, I will put some asymmetric graph here. And over here, I will do the exact same thing because it's the same match. But for B, I'm going to put a different asymmetric graph. If you put this systematically, the graph that you're going to end up getting at the end will have automorphism group isomorphic to the original group, okay? And this is how they prove it. Fruit proves it like this. The group of substitution proves it like this. Now, we asked ourselves this question. Can we come up with a definable version of this? How would the definable version go? First of all, we need to talk about definable groups. A standard Borel group it's a standard Borel space which also has a group structure. So it's a standard Borel space and it's a group structure. And what you want the group operations, the multiplication and inversion, to be Borel. Otherwise, it wouldn't have made sense to have a Borel structure on this. And you also, if you want to talk about this in the topological setting, let's say in the setting of topological groups, what's a Polish group? It's a group, but it also has a topology, and it's a Polish topology. And now your group operations are this time continuous because you're working in this different category of, like, you're working in a different category. Over here, your morphisms are the continuous maps, right? They're not measurable maps anymore. You want these to be not measurable, but continuous this time. So this is called a Polish group. This is called a standard Borel group. So now I know how to change this part. I shouldn't be talking about every group, but I should rather be talking about standard Borel groups or Polish groups. And then when you do that, you can actually generalize this. Now, start with a Borel graph, denote the automorphisms that are Borel maps by aught B, and denote the automorphisms that are homeomorphisms by aught H, okay? Honor Bilge is my master student. We proved the following. If you start with a standard Borel group, there exists a Borel graph on a standard Borel space such that this group and the Borel automorphism group are isomorphic, okay? So Fruit's theorem actually does generalize. And in the topological setting, it does generalize as well. If you start with a Polish group, then you can come up with an F sigma graph, sigma 02 graph on a Polish space such that this G and the homeomorphic automorphism group, so this is the automorphism groups which are homeomorphisms, these are isomorphic. Moreover, the homeomorphism, the set of homeomorphisms of a Polish space can be given with the submetric, a very nice topology. And well, but we're not taking that, right? Never mind. You're taking the compact open topology on this. And if you induce if you look at the induced subspace topology from coming from the compact open topology on this, then this isomorphism between these two can be taken to be a homeomorphism as well, okay? So this thing has a topology on itself. This thing has a topology coming from the compact open topology. So this isomorphism can be even taken to be a homeomorphism. So Fruit's theorem generalizes to the measurable setting, Borel setting, and also to the topological setting. Now, as was the case with the other results, we're still using Fruit's idea, by the way. Like, it's interesting that everyone uses Fruit's idea because it's so damn good. Like, it's a very creative idea. The problem is, when you look at the proofs of Sabidusi and Degut, for the infinite case, their arguments do not generate Borel graphs. Actually, their arguments generate like graphs which have very high cardinality, so they can't be possibly Borel. Now, we executed the same idea, but in order to make sure that everything stays Borel, you have to do a lot of coding arguments. Now, I wouldn't say that our argument is an ingenious one. It has very, very like deep tricks and so on and so forth. It rather has standard tricks, but done in a very not very, but slightly masterful way. Like, there are like coding tricks there. If you know enough descriptive set theory, you can get through this because you have to code stuff with the Cantor space and you have to make sure that things stay Borel. So you have to do certain parameterizations. You have to attach things in a very nice fashion to each other. So what we did is we still used the original idea.
There is a question.
Yeah,
Maybe what is the
I will answer that. Let me finish that. I saw the question.
What is the topology?
Yes, I saw the question. Let me finish this. Okay. I'm going to go back. So the thing is, like, we're still using the same idea, but you're just doing some standard coding tricks in a sense, and it kind of works. Now, over here, the question is, what's the topology over here? We don't have a topology over here because we don't have the topology over here as well. In this case, when you have a Polish group, there is the from the homeomorphism group of a Polish space, there's a topology coming from this. So there are topologies over here. But for this one, this is a standard Borel structure. This doesn't have a topology, and so we don't talk about a topology here. Now you can ask the following question: is there a measurable structure here? So it's not a good idea to ask a topology on here because we don't have a topology here, but you can ask the following question: is there a measurable space structure here that you can put on? I think there are many. There was a paper that I told my student to read, which kind of puts many different measurable structures on the set of Borel maps, like Borel automorphisms actually of a space. But unlike the topological case, it's not clear which one is the canonical one, because, you know, in those cases, like there can be multiple non-equivalent ones, and I couldn't choose, like I don't see which one is canonical. So over here, we didn't investigate whether this isomorphism can be actually taken to be something something stronger. Like this is a measurable structure, but on this one, which measurable structure are you going to put? Because there are many, you have to choose a canonical one. Now, it is possible that some of those actually work and the measurable structures are also isomorphic, but honestly, we didn't investigate that. Yes, so in the first theorem, the isomorphism is just an abstract group isomorphism. Now, as I said, it is very possible that if you put the right measurable structure on this one, it actually works. Indeed, I would bet that it works. Not too much money, but a bit of money that it works. But now you have to find the correct measurable structure on this, because as I said, there was this paper which suggests there are many of them, okay? So I don't know that, which is why for this one, we just left it as an abstract group isomorphism, okay? Let me check. Did I skip more questions? No. Okay, now I said 10 minutes and 10 minutes is about to done. And as I said, we just did a Borel implementation of this exact same idea. So we haven't introduced any new ideas, but just played with the old idea a little bit with the coding techniques. Here's the thing, due to the nature of the proof, our graphs always satisfied this. Their Borel automorphism group and their automorphism group ended up being the same. But it is easy to observe that you can actually separate this for many graphs. Like I can come up with many graphs where the automorphism group is not equal to the Borel automorphism group, okay? Like this can be countable, whereas this can be uncountable and this can be countable. Or worse, this can be countable and this can be countable, and I think this you can make this finite as well. So the next question that we thought we should investigate was the following, but it seems a bit difficult. So at the moment we're not working on this, and my student needs to graduate anyway. But here's a question that you can work on. Suppose that I give you two standard Borel groups. Can you come up with a Borel graph whose Borel automorphism group is the smaller one, and whose big automorphism group is the bigger one? So we know that we can separate these, but can you separate these in a given way? I don't know the answer. This is presumably a difficult question. At some point, I should start working on this, but at the moment, I don't know that. Now, as the last thing, here are two references. In this field, there are many papers. This is a recent field, so there are a lot of things, but I'm just going to give you two references, and I'll explain reasons. The first one is kind of the first paper that kind of, I would say, started this field. I mean, there were results before this, but this, you can think of this as the first paper. This was published in Advances in Mathematics 1999. And then Kakris from Caltech and Andrew Marks from UCLA, they are writing a book, okay? They are writing a book which kind of aims to collect all the stuff that has been done. I think I want to show you the book very quickly. So I'm just going to change this to, you can find this online. I think they're planning to publish this as a book from Springer based on the LaTeX. So this was in 2020. Maybe they updated this. This book by Kakris and Marks basically contains almost every result in this field that you can find, like their own results, all the new stuff that's been happening. And if you just look at the index, you'll see there are like many interesting things. For example, Brooks's theorem, Wissing's theorem, these are like classical theorems in graph theory. They have Borel counterparts. Sometimes they fail, sometimes they don't fail, blah, blah, blah. You have all these results. You have these G0 dichotomies, some basis and antibasis theorems. This is a very nice book if you're interested in this. Okay, so its title is Descriptive Graph Combinatorics. You can find this on Kekris's web page for free, and hopefully they'll publish it sometime. So that's that. I'm over time. I am sorry for that. As always, I couldn't manage time, and I'm sorry for seeing the question late and coming back at it late. So that's it. And if you have any questions, I can take it. Okay.